In this lecture, I'm going to do some proofs of some limit laws. And what I'm going to do is I'm going to first make use of an important inequality. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This is for any real numbers a and b. I'm going to consider various situations where I have a and b located at different places. Let's take a look at the part here, the a plus b in absolute value. That's the distance a plus b is from 0. Absolute value of a is the distance that a is from 0, and the absolute value of b is the distance b is from 0. So if we look at if a is negative and b is positive, then a plus b is somewhere between a and b. Okay, so let's say we're here. Say a plus b were there. Then on the opposite side of 0, you'd have the absolute value of a plus b. So this little amount there, let me use blue to illustrate it. This little amount here would be the absolute value of a plus b. Now, the absolute value of a is the distance from a to 0, and the absolute value of b is the distance from b to 0. Clearly, absolute value of a plus the absolute value of b is bigger than the absolute value of a plus b. Now, you could do various things like this. This happens to be where a was positive, or a was negative and b was positive. What if I move things around using blue pen this time? And let's say 0 is here. And this time, let's say a and b are here. Now then, the absolute value, well, a plus b then is going to be somewhere farther off down here. This will be a plus b. But since a and b are positive, that's equal to the absolute value of a plus b. And since a and b were positive, a plus b equals the absolute value of a plus the absolute value of b. So, we have in this case and you might be able to see if I do it for, say, a and b are negative numbers this time. Let's put 0. It's always referencing 0 because we're talking about the distance from these numbers to 0. Now, the absolute value of a is this same distance here. That's the absolute value of a. So if I were to put its number on the number line, I would try to take that much, put it over here, and let's say that's the absolute value of a. And then the absolute value of b would be this distance. So its absolute value would be over here somewhere. Then in this case, then if I take a plus b, since they're both negative, a plus b will be an even bigger number, bigger negative number. And then its absolute value would be the distance between that and 0. So if I were to graph that number on a number line, I would have the absolute value of a plus b would be the same distance on this side of 0. Hopefully you can see, I haven't drawn it very well, but in this case, since the negatives add up to this, these also add up on this side. So in this case, you're left with a plus b equals equals the absolute value of A plus the absolute value of B. So, for any real numbers A and B, the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. This is known as the triangle inequality. The reason why it has that name is because in a triangle, any one side is less than or equal to the sum of the other two sides. And this has a two-dimensional sort of analog to it. A secondary thing that we'll need is that if I have real numbers A times B in absolute value, this can be equal to absolute value of A times the absolute value of B. Now for the much awaited definition of a limit. The limit as x goes to A, f of x equals L means that for any real number epsilon greater than 0, there is a real number delta greater than 0 such that if 0 is less than the absolute value of x minus A is less than delta, then f of x minus L is less than epsilon. This may seem like a really confusing limit, but remember the one we did before on we're graphing a line or looking at the limit of a line. This piece right here says that x does not equal A. I don't care about x equaling A. The limits are never defined that way anyways. So, without further ado, let's use this definition here. And let me stop for just a minute. The epsilon, remember, that's the error. And the delta tells us the error in the x's. The epsilon tells us the error in the y's. So we'll start with the first one. Let's call it property of constants. So this one says if C is a real number, that did not work out so well. Then the limit as x goes to A, C equals C. And for the proof of that, it's pretty simple. For any epsilon greater than 0, the absolute value of C minus C equals 0, which is less than epsilon. So that takes care of that one. It doesn't even matter the delta I choose. You could let be any real number. All right, next. I don't know if it has a name to it. Let's write it this way. Limit as x goes to A, the number x, equals A. So for proof, let epsilon greater than 0 be given, and let delta equal epsilon. Then, when 0 is less than x minus a is less than delta, that's no different than 0 is less than x minus a is less than epsilon, since they're the same, which clearly implies that the absolute value of x minus a is less than epsilon. So that takes care of that limit. Let me prove the product rule for limits, and that'll be the last one for this particular video, and then I'll do another video with some more proofs on them. So let's see. Let's say the limit x goes to a, f of x times g of x. If I have that product, and I want to take the limit of that product, then what this particular product rule is telling me is that I can break this up into the limit as x goes to a of f of x times the limit as x goes to a of g of x, assuming all of these limits are finite. So, how do we do these kind of proofs? As always, we start with this statement. Let epsilon greater than 0 be given. What I'll then want to get to is to show that f of x times g of x minus LF LG is less than epsilon. This is what I need to show. Where the limit as x goes to a of f of x equals L sub f, limit as x goes to a g of x equals L sub g. So, as I mentioned, let me go ahead and start with that inequality and show you some of the things that I do to make this all work out. This epsilon is given to us in advance. So let's start with that that absolute value again. And I'm going to insert a couple of terms here, a little trick that we use. Looks like this. I'm going to subtract f of x LG, but then I'm going to add in f of x LG. It's a little trick. Next thing I'm going to do here is from the first two terms, I'm going to factor out f of x. And that'll leave me with g of x minus L sub g in parentheses. And I'm going to do something similar on the other piece. I'm going to factor out an LG, and I'll be left with f of x minus LF in absolute value. Now, the triangle inequality allows me to break up the absolute value according to that plus sign, and then we get less than or equal to f of x times g of x minus LG plus LG times f of x minus LF. Now, that was the triangle inequality there. The next property that I'm going to use is the one that I can break each of these absolute values up into a product. So I get the absolute value of f of x times the absolute value of g of x minus lg. And I'll do the same thing with the other one. I'll get the absolute value of lg times the absolute value of f of x minus lf. Alright, what I'm going to try to do is use this stuff here, the absolute value of g of x minus lg and the absolute value of f of x minus lf, are things that we have some knowledge about, because the limit as x goes to a of g of x is lg, and the limit as x goes to a of f of x is lf. So let me put this down here for a moment. We know for epsilon divided by 2 times 1 plus the absolute value of lg, there is a delta 1 greater than 0 for which zero less than x minus a less than delta 1 implies that f of x minus L sub f is less than epsilon over 2 times 1 plus absolute value of L g. So if you want to think about it, you can think for this particular inequality, this epsilon over 2 business is the epsilon that is given, and this is the delta 1 that is guaranteed by the fact that the limit exists. Now, on the other hand, I'm looking over here now at this f of x for epsilon over 2 times 1 plus the absolute value of f of x. There is a delta 2 greater than 0 for which 0 less than x minus a less than delta 2 implies that g of x minus lg is less than epsilon over 2 times 1 plus f of x, so that f of x is an absolute value. Alright, so let me go back up where I was before with this thing right here. I had gotten from f of x times g of x minus lg, and I got down to the line that has absolute f of x times the absolute g of x minus lg plus the absolute lg times the absolute f of x minus lf. I'm going to rewrite that particular inequality. Let me keep that stuff on the page if I can. All right, now, if I allow for my choice of delta, let delta equal the minimum of delta 1, delta 2. That ensures that both of the inequalities that I have, or both of the inequalities involving epsilon that I had before, this one and this one, will hold true, because this delta is even smaller than the two, or less than or equal to the two that I've chosen. So, as I continue this here, let me kind of move this out of my way. I'm going to get less than the absolute of f of x times, for g of x minus lg, I have the epsilon over 2 times 1 plus the absolute of f of x. And then I have plus lg times, what was the other one? Epsilon over 2 times 1 plus the absolute of lg. Now, ultimately, what I wanted to do is I wanted to cancel this f of x out, and I wanted to cancel this g of x out. The only problem with these is if f of x is 0 or lg is 0, then I couldn't just have that in the denominator. I would have a 0 there. So a cool way out of this is the fact that 1 plus the absolute value of f of x is always at least 1. 1 plus the absolute value of lg is always at least 1. Well, this is not a big deal because I can do one more step here. And notice that this is less than. And now I can do the absolute of f of x plus 1, just like my denominator. So I'm replacing a number with a bigger number. That's why this inequality is still going the way it is. And as you can see, the stuff that I'm getting here is working out perfectly. Because now I'll be able to cancel stuff. I'll do the same trick over here to the lg. I'll make it lg plus 1 times epsilon over 2 times 1 plus absolute lg. Well, now it works out perfect because now I can cancel. And I'll get equals epsilon over 2 for the first piece. And the same thing happens with the other one. That equals epsilon. So you'll get epsilon over 2 plus epsilon over 2 equals epsilon. So to reiterate, we were given epsilon greater than 0. We found delta greater than 0, where 0 minus absolute of x minus a is less than delta, implies that f of x, g of x minus lf times lg is less than epsilon. So we've proven the limit. I'm not going to do much more. I mean, this is a long enough video as it is. I'll do more examples in future videos.